how do you evaluate whether you should, I don't have any text on this side, whether you should pick, um, whether you should split it or whether it's good enough as it is, right? So this idea of impurity is kind of one of the main ideas they use, at least in decision trees. The idea is that we want the simplest model for every node, right? You remember Occam's razor, the simplest model is usually the best. We want a model where we can have a simple node, a simple model to do the classification, right? So if we get it to the point where, like I said before, all of the nodes in this data set, they all equal the same value, all of the labels, sorry, then that's the simplest possible, right? Because then we don't even need a classifier. We just say, well, everything is in this class, so class for this one equals 1, right? For this whole, all these x's, right? So that would be simple. So if you can make it so that you're maximizing that, then you'd get a tree where every block is obviously got a class. It's just you just read off the label from that table, and that's your classifier, right? There's no, you don't have to do that, but if you set that as a goal, then your tree will kind of be spread out. So this notion of purity is like, if this is that's why they call this pure. I don't like the term exactly, but it just means that it's uniform. Uniform, same, they're all the same. And so there's just different ways you could come up with this cost. So any cost function you can basically apply to these data points to penalize when they're not pure, right? So if they're all at the same label, that's easy. If they have some other value, then you just have to kind of do some math. How does this work? So we have 3 different kind of main ones we talk about here. So misclassification impurity is just saying you're having a probability of whether you're going to misclassify a data point. I'm dividing my terms here. Yeah, so in the next one I have that probability defined a bit better, so maybe we'll have this first. So let's define this probability of misclassification, where we're going to say we have our, if you remember our notation here that lets us say that the label just equals a value. So we're going to say basically count, essentially count, and come up with a proportion of how many data points have this class in the data set. And so all the people in our data set that are accountants, that's our class. We're saying what's the probability of us getting, of this node classifying accountants correctly. If it had if the data set, the person was in their accountant, we'd say, well, what proportion of the elements in the data set that are accountants did we get, right? We capture this portion of them. And that gives us a probability of us getting it correct. And I guess at this point it's important that D is the data set that's available at that node, right? Just trying to make sure it's consistent, because in our recursive algorithm, so it's just the proportion of the data points you'd get right if you just say, let's apply this class to the entire data set, right? And so we just talk about that the general cost, this misclassification impurity, would just be the probability. You pick the one that gives you the highest probability of getting it right, and then you basically say, well, what if I got that wrong, right? Right, so probability PWJ is the probability for that one. that we're getting it correct, and we pick the feature that we would, pick the data point that would give us the highest probability of getting it right, and we say, well, what if we got that one wrong, right? So that would be our cost in this way. So if we got that particular data point wrong, it would be that way of doing it. A better one, there's 3 different forms here. They're basically all very similar, but they just penalize being wrong in different ways. So the entropy impurity is a bit smoother, but it's kind of very broad. So in this one, like we said, we have that instead of you're just using the probability and like differentiating it from the maximum one, we compute the entropy of it, right? So if we remember from the probability review lectures, the entropy is just this other kind of inverted form of probability. So as the probability goes down, the entropy goes up, but it kind of behaves a bit better in a linear kind of smooth way. So we use this as our cost, right? As the entropy goes higher, if all the labels are the same, so if we've got a completely 100% pure subset of data, then the cost under this would be 0, because our probability of getting them right would be 100%, so our entropy would be 0, because it's perfect, there's no noise, essentially, right? And when the maximum cost we'd get here would be when all the labels are equal, right? So if you've got 10 data points in a table, and there's 5 labels, so every two data points have the same label, so they're all uniform essentially. Then you get this maximum entropy. So be like, that's really bad. You basically picked a subset of data where all the data points have like the labels are equally spread across the data points, so it's kind of not very informative. Whereas you get 0 when they're all the same, and you've got a perfect tree. So that's the second one. And then yes, Laurel Murray is asking about the DL and D left. That's right. That's the left part and right part of the tree. Given your current data set, you divide it into a left and a right division. So the third one, which is kind of the more popular one, because in between the other two, is this Gini index, and it's used in a lot of different areas. So this gives you basically the expected error rate at that node if you picked it randomly. So it's not just assuming that you're picking the worst case or the best case like the other two. Saying if you randomly picked a node in the tree, then how likely would you be to get it wrong, right? So you're, I guess, looking at, for all the labels that are for data points that are not the same, add up all the ones where they're being mismatched. So the way these ones look when you put them together, say you've got the probability of this particular data point being right or not, then you basically are turning, because you've got a probability of getting it right, just in terms of all the data and the way your tree has been built, but you're trying to build a cost function that'll help you estimate whether you should keep it or not, right? And so you want ones that behave in a different way. That's kind of, they're going to turn that probability into a cost that you're going to use as a threshold. And so what they do here is that they make it so that either way, if it's if the probability of getting it right or of getting it wrong are kind of like high or low, then well, I guess it's the probability of it having that label, right? So right. So our PWJ, I was confusing them up here, is saying that we're saying what's the probability of the data point having this label J, right? So if it's 50-50, then the probability of the data point there being told that it's class J, um, then we wanted to basically give us a very high cost. We don't want to have nodes with subtables where there's just an equal chance or a uniform chance that this point could have any particular class. We want it to either be very sure, like sure that it's either in the class or not in the class, right? We'd rather have certainty, right? So we have basically a cost function that is low when the model is very certain, either it's like it's not in the class or it is in the class, and when it's uncertain, we want something high, right? So those three different forms we have there do this. That really naive error rate one is this very sharp thing. So you'd have these weird behaviors here if you're saying, you know, it drops off dramatically if you're just above or below 50%, which is not really what we want. And the Gini one has nice properties that people like using just because it's smoother that way, but entropy is very similar. So you essentially want to say that, yeah, and if you're anywhere near this kind of uncertainty thing where the point could be in the class or not, we'd rather have a high cost. And if that's a high cost, then we split the node. That's kind of our algorithm, right? We don't want it to be too sensitive to just being off by a couple data points. Right, so whatever the cost function is, and you can define other ones, but you basically want something like that form where you say you're penalizing uncertainty and rewarding certainty. Now you're going to have a cost function, and you're going to use this to determine whether you should split or not. Right? And even once you're deciding to split, what's the value you should split on, right? Yeah, for picking, so Taryn's asking, we want to lower the cost of the split. Once you have the split, once you're deciding to split or not, because remember, if the split cost is low, then you could say for one of the classes it'll be high, and you'll say, well, they're all pure, right? If it's basically pure, then you don't want to split at all. But if you're going to split, then you want to choose a split where the costs are going to be low, right? You want to pick one that's going to be very decisive. You're going to pick it here, and it says, okay, I'm going to pick something that has a lower cost, and all the data points on this side are in one class, and all the rest of the points are maybe in two classes, right? You'd rather have a split that's really logically sensible. And so the way we're going to choose the split value is by doing that, right? We're going to like compute the cost for the overall data point, right? So now remember we're in this situation where maybe we've come down the tree at some point. Now we're at this node and we've got a table of values, right? And we're going to split again, right? So this is D, this is DL, this is DR, and now the question is just what value do we split on, right? And we want to say, you know, feature something is greater than something, right? We have to pick both of those. Here we're assuming that you chose the feature already, so that's known. We've got that. Now we got to pick K, right? And the way we're picking K in this way is kind of the simplest thing you can do. Say compute the cost for the overall data set, which is the input here, kind of your whole table. Compute the costs for the subset, so you propose a split. And these are just data points, right? So you don't even have to have a rule this way. You can just say, well, these points and those points. We usually cast it in terms of like an actual logical rule on the value of a feature. But whatever way you've divided them, you now have two smaller subsets, right? And as someone was asking before, right, it has to be true that D equals DL plus R. There's no leftover. You compute the cost on those and you weight it by the proportion, and then we'll say that's going to be the cost of this split, right? And obviously, if you change the rule here, right, so we could look through, you know, a bunch of different values, right? We're going to go through all the values of whatever this feature are. Each of them will give you different costs, so you can pick the K to optimize this, right? So we want to maximize the change in the cost here. Maximize the change. Well, because the change would be a reduction, right? Because we're taking the original cost of the data and we're subtracting the costs of the lower ones. So we want to make this change as big as possible, right? right? And if you're using entropy impurity, so some people like using that one. The Gini index is very useful and logical to people, but if you're using entropy, then what you're essentially doing here is maximizing information gain. So you can do a information maximization thing, and just say that basically you're giving us the probability of the best split that gives us the most information about the difference between these data points. So somebody had a question about that error rate from the previous class. I think the error rate was just this misclassification impurity one, because you're basically getting how often did you get it wrong, right? That's what that error rate one would look like. Yeah, and as we're saying, you're doing this at every node, right? So as you're growing the tree, once you get to this tree, you have to make this decision, compare all the values, decide the split, and then decide what the feature should be, and then decide what the feature split should be. So there's a lot of components to it. It can get expensive if you're going to try to really be optimal. And so again, this is the kind of classic original kind of decision tree algorithm. And what we're going to keep talking about is like additions to this, ways to improve it. But all of those other algorithms are kind of based on this idea of a decision tree. So another decision we have is when to stop. Right, so like we said, the simplest way to decide when to stop is when all the data points have the same class. Right, so if pure equals 100%, then they're all exactly the same. This one would kind of overfit. So when we're talking about overfitting impurity, you definitely would be, right? Because maybe it's not the best idea to have every leaf just having one class. Probably what will happen is that a lot of your leaves will only have a single data point, right? Because that was the only way to divide them up, right? And maybe this one's now got still a big table, but there was only one guy left with that label, right? If you think about optimizing and drawing this tree, once you realize you've got a leaf that's only one node, and you're like, okay, now I'm kind of overfitting to this, you'd be like, oh, I wish I'd just gone back and changed that decision, that split, you know, and pick something else, right? So that's why it becomes NP complete, right? Because the optimal way to do it is when you notice this, you say, okay, stop, delete this, go back here, pick another one, and you keep searching up and down, up and down. So optimizing it perfectly is very expensive, so we don't do that, basically. But you want to come up with heuristics that let you grow it in one shot, and it's going to be pretty good. And we'll get better and better ones as we go today and tomorrow. What else do we have here? So you could, other things you could do rather than just waiting for it to be pure, you could look like for the minimum reduction in cost, like we're talking about. If that cost reduction is not big, then you just stop. Right, that's basically this one. If the delta cost that we talked about there before, if it's less than some threshold, or so less than 0.1 or something, then you say, don't bother, right? It's not really helping much, we'll just leave them all in one leaf, right? Or, right, a more classification way to do it. Remember, you have your train, test, and validation set. You could have your validation set where you're all basically checking it as you go down the tree. You're training on the training set, so you're actually splitting on the training data. But your validation set, maybe your 10% of your data, you use it to judge whether you should stop or not. And then in the end, you report your result in your test set, right? So that's a very sensible thing to do too. Great. So on the channel, on the side channel, we're having a crash course in EC 606, computational complexity. Yeah, don't worry about it. It's the NP complete and NP are not, I think, on this course. I'm saying them for the purposes of this course. What we're talking about is just that it's intractable to optimally recompute this, and it's because it requires you have to go over all combinations of the optimal kind of series of choices and things. In 606 and in some other theory, there's different categories of how to break this down. and figure out whether it's just hard or whether it's really infeasible in a long period of time. But it's kind of outside of scope of this course. Okay, so the fourth option we had there was minimizing some other criterion, so you could come up with a more general formulation for that. How does this one work? So we've got our cost that we computed before on the current node, and we can basically put another penalty or regularizer on the whole thing, right? Because we'd say that in size, right, okay, yeah, I was thinking, did we mean depth or anything else? It could be anything, right? So you can come up with the saying, I don't want the tree to be too deep, right? Or too wide, right? And so you say, I don't want, you could mean, like we said, if you hit 10 levels, you get to stop when you get to 10 levels deep, but you also just put a penalty like this and say, okay, I'm going to put a penalty of 5, and on the size being the maximum depth right now. So the deepest possible, node in the tree, whatever it is, it's going to be our depth of the tree. And it could be there's some parts that are shorter, but there is some node that's like 10 down, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? You could say, well, I don't want it to be too big. So this way you're putting a size saying as the size gets bigger, the cost just gets higher regardless. So even if you got a really low cost split, eventually this will dominate it and you would stop, right? Right, so as we talked about before, this is another example of a regularizer that stops it from overfitting, right? Because if you think about what is an overfitting tree, if we have this tree that's going very down specifically and every single node has a single row in it, or a very small number of rows, we've basically overfit, right? Because there could be, very similar patterns now that are in different parts of the tree, and they're now disconnected, right? And we might not give them the same class, right? We'd rather have all of the data points that are in one class, at least in the same node or near each other, because hopefully we're going to get a better function then. So a regularizer is anything that helps us reduce overfitting, right? And so this penalty will help us do that, because remember, as the tree gets bigger, the cost will go up, right? And we've been trying to minimize the cost. So we would stop, right? So like we had in them, if we're using this rule to stop when the cost is below a certain level for a split, then this would make that harder, right? Right, so depending on which cost function you're using, there's kind of different meanings for this. So I guess entropy impurity is like related to information representation. So how much information a distribution can represent in terms of like in a computer, right? In bits. And so if you use that, then essentially this cost function as a minimum global criterion is giving us like a minimum description length. Like what's the shortest way you could almost encode this data or like compress it, right? And so you're saying, optimize it so that you're giving a code that's really compact, right? You could think of that as a compactness thing too, because if you had the smallest number of rules here and you come up with a perfect set of divisions so that it's basically your data in chunks with just those rules, that would be the minimum way to describe it or compress it. So these are all just goals that basically you put them as costs and you're using that to optimize. Okay. Oh, that's a good question. So Rahul is asking, can depth exceed the number of features in the data set? So let's think about that. Could we? So how many features? Let's say we've got n data points equals 100. Let's say features equals 2, right? And so we always split on feature 1. It's less than 5. And we have some data here, right? And now we're going to split on feature 2 and say it's less than it's greater than 100 on this side, right? So we don't know how big these are now, but we could have, you know, any number of data points in here still, 50, 5, 5, 6, 7. Oh. I need another split, right? So we could have like that, but then once we're here, we could just split again, right? So there's no reason you can't split multiple times on the same feature, right? These ones are all on this side. These are, I said these were all greater than 5. So on this side, they're all less than 5. So when I split on F again, I could say, well, now they're all less than 2 on this side and greater than 2, but less than 5 on that side. So they build up, but there's no reason you can't use the features multiple times. So you could go down all the way. The only limit is that if you think about from trees, right, there can only be how many leaves? What's the maximum number of leaves we could have? 100, right? So the number of leaves in the tree is always going to be less than or equal to the number of data points, right? Why can it be less than the number of data points? Because maybe this one's got, you know, 2 data points in it, right? So it counts for 2, right? But a lot of these ones might be only 1. Ideally, you don't usually want to do that. We'll talk about one algorithm where you actually always want to go down to 1, but usually you want them to be higher, maybe 100, maybe 1,000 in each leaf. But yeah, there's no restriction on how far you can go down except that you've run out of data points. Right? Just remember you're partitioning the data every time you split. So the n at every one of these levels is less than before, right? Great. Yeah, and so the longer SFE is asking, like the deeper you go into the tree, it takes longer. So you're making, if we're doing this full decision tree thing here, right, where you're optimally trying to choose the right answer at every point, you know, that's expensive. You've got to like compare against all the features and compute it, and then you're doing it at every one of these nodes. So it actually gets really, it adds up to optimize this. Now, when people came up with this algorithm, I guess in the 80s or 90s, expensive seemed like a big deal for this, but it's not expensive in like deep learning sense expensive. It's very fast in sense of that because it's a bunch of these numbers that are computed, and these ones can be done in parallel, right? Because if you think about these two data sets, once you've split it, these are completely separate, right? So you can definitely do a lot of these things at the same moment because once you've partitioned the data, they're completely independent now, right? And so all this entire tree is independent of this tree now, so all this can be parallelized. So it's a bit excessive, but yeah, you do compute at every step. So